forgot to combine these two videos, but that's okay. That's fine. It was a long problem. So, given the following system equations, once again, I have more unknowns in here that I need to solve for. It doesn't tell me how to solve for them. It doesn't tell me what method to use. I need to come up with it. But here it's asking for if the system is consistent and how many solutions we have. So the easiest way to do that, or in my opinion, the best way to do that is using Gauss elimination. So I'm going to go ahead and write my system of equations and my augmented matrix as an augmented matrix. So it says find a value A11 such that the determinant of A is equal to 0. Oh, never mind. We're talking about determinants. Wrong problem. Here's A. Okay, so I'll do the shortcut method. Since it's a 3 by 3, we can. We can use a shortcut method. So these three diagonals is going to be 2A11 plus 20 minus 6 minus these other three diagonals. 3A11 minus 5. 2 times 2 is 4, times 4 is positive 16. If I want that to be equal to 0, that means 2A11, that's 14, plus 14, minus 3 times A11. Minus plus minus, that would be negative 11 equals 0. So that means negative 1 A11 equals 14 minus 11 is 3, negative 3. A11 equals 3. So I solved for a value for A11. It says if the system is consistent, it means it has at least one solution. How many solutions for the system? If my determinant equals 0, and system is consistent, then I have an infinite number of solutions. Infinite solutions. There's my answer. Here's my justification. System is consistent, determinant of A is equal to 0, there's an infinite number of solutions. And you should see that in the notes. In week E material, you can see that table that shows all of the bullets that show essentially all the things we can conclude given one piece of information. One piece of information being that our vectors of A are linearly dependent and independent. These vectors are dependent. They're dependent because my determinant is equal to 0, which means if they're dependent, I have one of two scenarios. It's either infinite solution or no solution. The fact that it's consistent means that I have an infinite number of solutions. B, find a value of A11 so the determinant of A is equal to 1. Negative 2, 1, negative 2, 1, 4, 3, negative 1. Okay, so I need to find a determinant of A so that now my determinant is equal to 0. And I'm going to do this using cofactor expansion because I'm going to have to solve for the system equations. Note, my determinant is not equal to 0. Therefore, I have a unique solution. Therefore, I have one unique solution. My vectors are independent. All these things I can conclude knowing that my determinant is not equal to 0. Okay, so I have to solve my system using the inverse of A. So I'm going to go ahead and do my cofactors. C11 equals positive, negative 2, 3, 1, negative 1. So that's equal to 2 minus 3 equals negative 1. C12 equals negative 1, 4, 1, negative 1. And I'm starting these out first because I know I'm going to need them for my cofactor matrix. And I also need them to find my determinant, solving for A11. So this one is negative 1 minus 4 equals negative 5, made positive because of this number out here. 1, 3 is negative. 1, 4, negative 2, 3. There's less zeros in this matrix, which is kind of sad. I like the zeros. 3 minus negative 8, which means it's going to be 11, made negative by that value. Oh, no, that should be positive. So that felt wrong. Okay, there's my cofactors for my first row. I want to go ahead and find my determinant now. Determinant of A is going to be A11 times negative 1 plus 5 times 5 minus 2, or plus 2, plus negative 2 up there, times 11. So negative A11 plus 25 minus 22 equals 1, which means A11 equals this. It's going to be 3. So minus 3, it's going to be 3. No. It's going to equal 2. I was going to say, that can't equal the same number. Forgot this one here. So 1 minus 3 is negative 2. There we go. A11 is 2. Okay, which means, continuing with my cofactors. So this is now 2. Continuing with my cofactors, it means it's going to be 5, 3, negative 2, negative 1. So negative 5 minus negative 6 equals 1, made negative by this fun cofactor adjustment out front. 2, 2, plus 2, 4, negative 2, negative 1. Negative 2 minus negative 8, that one's equals 6. C, 2, 3, minus 2, 4, 5, 3. Checking my answers, make sure I'm on the right track. Yep, we're good. 6 minus 20, so for negative 14 turned positive from this adjustment up front. And then my last row of cofactors. 3, this is row 3, column 1, so 3, 1. Plus, 5, negative 2, 1. 5 minus negative 4 equals 9. Nope, I lied. Minus 4. There we go, equals 1. C, 3, 2. Minus. There we go. 2 minus negative 2. There we go. This is 4 adjusted to the negative. There we go. Now we're on the right track. Plus. 2, 1, 5, negative 2. Negative 4 minus 5. Negative 9. There we go. Okay. So there's all my cofactors, which means A inverse is going to equal 1 over 1, because the determinant is equal to 1. That's what I forced it to be. And then I take all of these cofactors and transpose them. So my first column becomes negative 1, 5, 11. My second column is negative 1, 6, 14. My third column is 1, negative 4, negative 9. So there's A inverse. If I want to solve my system using A inverse, I'm going to go ahead and multiply that by B. So here we go. So I only have column 1, row 1, 5 minus 3 minus 2. That equals, I'll write it in a separate matrix because I know I have to anyway. Or I know I should anyway. That equals 0. Then I have negative 25 plus 18 plus 8. That should be 1. Negative 25 plus 26. And then negative 55 plus, oh gosh, 14 times 3. 30, 42. Yeah, 42. And then plus 18. I will do that on my calculator just to save you guys from my mental math. Once again, not impossible to do without a calculator. It's just faster if you have one. Okay, there we go. There's x. I have solved my system of equations. I can go ahead and verify that by saying ax equals b. If I have time, I can do that. If not, totally fine. Okay, there we go. Problem 3, version B.